Okay, there's one topic I wanted to finish up in section 2.2 on matrix vector multiplication. Okay, and that's the concept of actually viewing matrix vector multiplication as a transformation. So I want to talk a little bit about that. In general, a transformation T can be viewed as mapping from N space to M space, a space of dimension N to a space of dimension M. So a simple example of this would be, and remember this notation represents an ordered tuple of n tuple of or a set of n numbers, n real numbers. So let's consider an example of a transformation from three-dimensional space x1, x2, x3 to two-dimensional space x1 plus x2 and then x2 plus x3. So this is an example of a transformation from R3 to R2. Transformations don't have to be between spaces of different dimensions. They could be between the transformations, both in three-dimensional space or both in two-dimensional space. So we're actually going to focus on matrix transformations. Not all transformations can be represented as a matrix transformation, but of course we're covering matrices, so these are the ones we're going to focus on. So I'll define a matrix transformation, TA from Rn space to Rm space is defined by matrix multiplication. TA on X is equal to matrix A times the vector X, and we learned how to do this matrix vector multiplication last time, okay, where A is of dimension M by N. Okay, so X has to be of dimension N by 1, multiplying by an M by N matrix would yield a vector of dimension M by 1. So let's look at a couple of different examples. Okay, where we'll look at examples in two-dimensional space, at least initially, where I'll define a vector X consisting of coordinates X and Y. So this would represent a point at location X and location Y, okay, or the corresponding vector from the origin to that point. So a couple of simple examples. If we let A equal 1, 0, 0, minus 1, then AX will be equal to X and minus Y. Okay, so a corresponding graph would be like this. So here's the original point, X. Then the transform point, AX, has the same X value, but has a corresponding Y value that's equal to the Y value above. So this would be minus Y. So this is the transformed point. Okay. This represents a reflection transformation about the x-axis. And actually, if we changed this element of the matrix to -1 and this one to +1, the corresponding transformation would be a reflection about the y-axis. And this is a transformation from R2 space to R2 space. It transforms a two-dimensional vector into another two-dimensional vector. Again, sometimes the spaces will be of different dimensions, but they don't have to be. Okay. Another example, try and squeeze a few more examples on this slide, would be where A is equal to real number A, 0, 0, 1, and then carrying out the matrix vector multiplication, AX will have A0 times XY, we'll get AX, and then here we'll have 0, 1 times XY and Y. So this represents a scaling along the X component. So in the corresponding graph, if here's the original component X with coordinates X and Y, the transform component is going to have the same Y value, but an X value equal to AX. So this is the transform point or the corresponding transformed vector. Same Y value, but a different A value. This represents an expansion along X, at least if A is greater than 1. If A is less than 1, we actually get a compression along the x-axis. A similar example would be something like this. 1A, 0, 1. And then now AX would be equal to, we have 1 times X plus A times Y, so X plus AY. And then the Y component is not changed. So in this case, if this were original point X and Y, okay, then the new point would be, again, it's going to have the same Y value, but it has a different X value. So it's X plus AY. So this distance is AY. So this value is actually X plus AY. This looks similar to the case above. It is different because now the expansion along the x-axis actually depends on the y value. For an original point, let's call this x1 and ax1, for original point in this position x2 with a greater y value, then the expansion ay would be greater because y is greater, so the product ay would be greater. Okay. Whereas in the previous case, if we had an x2 here, the expansion would be exactly the same. Here the expansion depends on the y component. So this is called a shear transformation. Okay, look at a couple others. Example D, where A is equal to 0, 1, minus 1, 0. Okay. AX then is actually equal to minus y x. And so if I sketch that transformation, okay, here's the original point, x, y, and then AX component, the x value is the negative of the y value, so I'm going to keep this distance the same, minus y. and then the y value is equal to the x value, which is here. Okay, so this is the transformed component. It's not obvious necessarily what the relationship between, what the geometrical relationship between these 2 points is. But if you actually draw this vector and draw this vector, actually I haven't quite drawn these to scale because I know that these links are actually the same, because the square root of the sum of the squares is the same in both. In the original vector, it would be square root of x squared plus y squared. In the transform vector, it's the square root of negative y squared plus x squared. So these links should actually be the same. I've drawn them, so it appears that they're different links. So they should be the same. But if you actually calculate this angle here, this turns out to be a 90-degree angle, or a pi over 2 angle. So this corresponds to a multiplication of a vector x by this matrix, corresponds to a counterclockwise rotation of the vector by pi over 2 radians, or 90 degrees. Okay. Another one, if a is equal to all zeros, then ax quite simply is the zero vector. That's called the zero transformation. If a is equal to a matrix that has all ones along the diagonal and zero everywhere else, this is known as an identity matrix, and it will pop up quite frequently in the work to come. Then ax is equal to x. There's no change in the point at all. Again, we can view any matrix multiplication as a transformation from one space to another. Let's go back to that first example we looked at, where at first I introduced the idea of a transformation, where we went from 3 space to 2 space. If I define A like this, then this is, of course, a 2 by 3 matrix. So X has to have 3 components to be compatible for multiplication. Now, if you multiply this row, do the dot product of this row of A by this column vector, we'll get x1 plus x2, and the second row times the column vector will get x2 plus x3. So I define this, talk about this actually as a first example of a transformation, and that particular transformation can actually be represented by a matrix multiplication as well. So here we're mapping from a larger dimension space onto a space of fewer dimensions. Of course, you can have mapping that goes from a smaller dimension space to a larger dimension space as well. I think I'm going to wrap up this video. In the next video for today's lecture, we'll go on and we'll talk about multiplication of matrices.